Welcome to this third set of lecture videos for Physics 4C. In this lecture, we start our coverage of geometric optics, looking at the optical elements, lenses and mirrors, and introducing the technique of ray tracing to help us develop our intuition for the images formed by lenses, and sometimes mirrors. Before we jump into the lectures, there are some formulas that are derived in the textbook that you will need to know to solve some of the homework questions. In the interest of time, we won't separately derive them in the main set of lectures. Do please read about them in the textbook, and most importantly, make sure that you know where to look them up when and if you need them. What you see on the screen here is the formula relating the focal length of a spherical mirror to the radius of curvature of the spherical mirror. That is, F is equal to R over 2. I do recommend looking it up in section 2.2 and following the geometric reasoning, including the role that the small angle approximation, also called paraxial approximation, plays in the derivation and how that is related to what we call spherical aberration. The analysis of refraction on curved surfaces are quite a bit more complicated. I'll admit that I have done lectures on this where I have made mistakes. Fortunately, replicating these lines of reasoning is not necessary to tackle most of the interesting problems in geometric optics. I do want to make sure that you know where to find the formulas for the image formed by a single refracting surface in section 2.3. As you look at these formulas, specifically equation 2.11, please make sure that you understand the sign convention for the radius of curvature and the image distance covered at the end of the section. While not many problems require use of this formula for solution, when you encounter those problems, make sure you can find this formula. Finally, the lens maker's formula is last of these formulas that you will need to know to solve some homework problems. Your textbook covers it alongside the derivation of the thin lens equation. Our main lecture will cover the thin lens equation and make an extensive use of it. Lens maker's formula for calculating the focal length of a lens, however, rather than experimentally measuring the focal length or somehow being given the information about the focal length in the problem, this is not very often used, whether for your homework problem solving or in practical lab work involving lenses. Nonetheless, make sure you know where in section 2.4 you can find the formula, equation 2.20, for those situations when you do need the lens maker's formula. With those formulas out of the way, and you knowing where to find them when you need them, the main lecture will cover these topics that are both important in your conceptual understanding of geometric optics and solving practical problems involving lenses, and seldom mirrors. We will first talk about what an image is and what distinguishes real images from virtual images. Then I'll demonstrate a PhET simulation that can help you build your intuition for geometric optics. Then we are going to see the principal rays used in ray tracing demonstrated, followed by the derivation of the thin lens equation by using the geometries illuminated by ray tracing. In this set of lecture videos, we will cover the standard single lens example and use the example to derive the linear magnification formula. We have more examples involving lens optics to cover in our next set of lecture videos on geometric optics. And we will then also cover examples involving multiple lenses. Oh, and as you will hear me mention a couple times in the lecture, the main reason I avoid mirror optics is because drawing clean ray diagrams for mirror arrangements are difficult. And you can always solve mirror optics problems by first turning them into an analogous lens arrangement. In practical applications, there are devices that preferentially use mirror optics, such as the Newtonian telescope, because using mirrors avoids certain complications such as chromatic aberration. I guess the first thing we should go over is the concept of image. It's you'll find that if you look in your textbook, it's actually not defined anywhere. So if you go to the, let's see, if you go to the end of the textbook, and I did that because I was trying to write down, when you look at the glossary, it does talk about things like image distance. But they will never really take the time to define image. It's sort of, I think there's a good reason for it, but let's try to go through what an image is, so, because it'll be an important part of what we are talking about it in this chapter. So here's a maybe most common example of an image. I have a plane mirror here. Everything you see in this plane mirror right now is an image. So let me put this right here. So for people who are sitting along the center column, you are going to see yourself mostly, maybe your neighbor. People who are on this side, you'll see that other side. So let's see. Function, do you see Jason? Yeah. Okay, Jason, you see a function? So what you are seeing in this mirror is an image of function. So where does it appear to be? If you are, caveman and you didn't know what mirror was, as you look at this, where would you think he was? Like through here, at some far distance away, you might think this is a transparent window and there's a person sitting over there, right? So in short, that's an image. Image is a construct or abstract idea we use to describe when some arrangement of light appears to be coming from some place that it's not actually coming from. So it is actually coming from function's location. The ceiling lights are reflecting off of him. Some of that light is coming to the mirror. It bounces according to the law of reflection that you know, and it somehow reaches you or reaches Jason. That's how you see those rays of light. But if you ignore how this optical element is modifying the light, it appears to be coming from a distance, coming from a particular place. So this, let me draw a diagram because it's hard to just point at things. So if you have, let me draw the mirror here. If you have a mirror, for example, and you have something or someone over here, I guess I'll draw a triangle. Then when you look at this ray that's coming from this point on the triangle, this ray goes in many, so there's the light from here goes in many different directions. It's what we call diffuse scattering. The light that's hitting most of the object, it scatters into many different directions. I guess the contrast would be something that's in a very directional. Like most of you cannot see this laser beam until I shine it directly into your eye. So this would be a single ray of light, literally single ray of light that you won't see until it diffusely reflects from my hand. But in everyday life, in most cases, you have diffuse reflection and light rays are going kind of everywhere. And for a particular person here, this particular ray of light would hit off of the mirror, and it undergoes reflection the way we were describing last week. So angle of incidence equal to angle of reflection, and someone who's present here sees this ray of light, and to this person, to this observer, this ray of light appears to be coming from this direction. Appears to be coming from this direction that you would get when you extend this ray of light.
Now, when you're just looking at it, you will see that there's a question that we left off unanswered. So, Jason, once again, sorry, I'm sticking with the example I've used. When you see a function in this mirror, does it appear to be at a particular distance? Would you say he's a, very, very, like, would you say that you could not tell if he's right here or if he's very, very far away? Or is there a very particular place where he appears to be? Okay, far away as in somewhere like over here, back here, right? But one thing you wouldn't say is that you do not say that you would not say that you couldn't distinguish whether he's way over here versus whether he's over here. You can clearly see that he's not very close to the mirror, right? So when you look at your images in the mirror, they actually appear to be at a particular location, not just one point along a line, but a very specific point along this line. And when you look at this tracing of a single ray, that is not what you get, because with this single ray, like this ray could be coming from anywhere along this spot. But somehow, intuitively, when we look at things in mirror, what you know intuitively before I prove it mathematically or whatever, is that the image of this point is kind of here. Like this is where the image is. It's not just anywhere along this line. So how would you get that? How would you sort of prove that the rays of light that's reflecting off of the mirror, they do really appear to be coming from this single point, not anywhere along this line?
Is that because they have the same distance?
Okay, it happens to be the same distance here as here, but that sort of sounds like a made-up rule to me. As in, the rule makes sense, right?
That's the virtual image, right? The one that we see.
I'll get to virtual soon enough. So what Samuel was saying was that maybe the rule is that this distance is equal to this distance, which is true enough. But what I'm looking for is I'm looking for a general procedure. I want to find those procedure or rule that I can use even for lenses, even for things that's nothing like a plane mirror. So this is what the problem comes down to. Problem comes down to trying to define a point. What geometric object do you need to define a point?
X and Y coordinates.
Okay, if I have two coordinates, I can do that. Let me rephrase my question. I have one line already, right? And the way this point is going to be defined will have something to do with this line. It'll be along this line. So what additional thing do I need in addition to this line in order to define this point geometrically?
Another line.
I need another line. When you have two non-collinear lines, where they cross can define a point. So that's what I'm going to need for here. I'm just going to need another set of lines. So graphically, this is what it is. I drew one ray. So what I should do is I should draw another set of rays. I should draw maybe another ray that reflects from not this point, but from this point. Let me do it in different color. So the ray that's reflecting off of from here, it must have traveled in straight line from this point to that point where it's reflecting, right? I can draw this because I'm supposing there's infinitely many rays here. I never drew a comprehensive list of rays. I just drew a few as a representation. I'm just identifying one more that makes it convenient for me to do this. All right, this ray will undergo the same reflection under the law of reflection. And because this angle of incidence is smaller, this angle of reflection will also be smaller. So it should be drawn at something like this. No, I'm trying to draw this correctly, right? Because of the difference in angles, you see they are diverging. right? As they come to an observer who's somewhere out here, the two rays are diverging. Now what you see is that when you trace this ray back, they will cross at some point. And if you drew this drawing correctly with rulers and protractors, you would see that they cross at the point where you are supposed to find the image. Yeah?
What if the second ray that you drew was like pointing that way?
Why would you?
Because you pointed them both to the right, but what if you pointed one to the left? You would get
You mean if I have this ray?
Yeah.
Well, the observer here will never see this ray, right?
Yeah.
But you know, even for this ray, if you draw it correctly, it should appear to come from this point. That is actually an amazing thing about image. Any light ray that's coming from this object, so let me actually use the term, any light that's coming from the object, and it first hits the mirror, and then goes to any observer, will appear to be coming from this image. So we will treat image, as far as optics is concerned, almost the same as object. This is a source of light, or we treat it like a source of light. Any light that first go through some particular condition will appear to be coming from this thing that we are going to call image. Yeah. So yeah, does that answer your question, Javier? Yeah. So you can do it for any of the infinite rays, and if you drew it correctly, you'll find that they all appear to be coming from the single point. That's how we locate the image formed by a plane mirror. And I won't go through the exercise because it'll be intuitive to most of you that the location of image is at an equal distance. You sort of intuitively know where to find it, right? Yes. So what I'm going to do instead is spend a little more time talking about image formed by slightly more complicated objects later on. A spherical mirror, curved mirror, and a spherical refractive surface. And yeah. So, all right, so Samuel mentioned the phrase virtual image, right? Yes, you said this is where the virtual image is, and you're right. This is a virtual image. What did you mean by virtual?
It has the same shape, the same.
Okay. Have you seen what a real image is? Okay, a lot of people here would not have seen real image. So this is what I want to go over now. It's a distinction between what a real image is and what a virtual image is. It's a very simple distinction. I want to put this somewhere where almost everyone can. So with a plane mirror, you will only ever see virtual image. You won't see real image. So let me take this away. This is something called the Fresnel lens. What it is it's a magnifying glass. Like you can see my face magnified, right? Kinda. I can see it. Do I look like a magnified face? Yes. Okay. All right. So all it is. It's a magnifying glass. That's really what it is. It has a special construction that allows it to be super thin, but just think of it like a magnifying glass and you won't be wrong. All right, so it's a magnifying glass. And right now what you're seeing is a virtual image. It's just like the thing you see in the mirror, not that different. So this is a light bulb that we actually use for magnetism in 4B, but it'll work well enough for what we want to do, I think. So let me turn this on. And you can see the light bulb. And let me just to see how, kind of have to know the focal length of this thing. All right, so right now you are seeing virtual image. For those of you who can see it, let me see if I can get it to project a real image. Sorry, to be way back here to see. All right, yeah, I think that's good enough. All right, so what I'm going to do is I'm going to flip it around. So when you're on this side, so you see the light bulb either right side up or upside down. Big deal. Sometimes it looks big, sometimes it looks small. So what I want to demonstrate is the actual difference between real image and virtual image. I can do it more easily if this room isn't so bright. So let me bring down the blinds to do that. So let me turn off everything here. I think that'll be dark enough. I'm going to flip this around so that now the source of light is over here, and I'm going to try to form a real image on this side. All right. So the optical quality of Fresnel lens isn't very good. So this is the best I can do. This is the real image of the lens, not lens, of the filament.
But it's still upside down, right?
Yeah, it's still upside down. So this is what I want you to imagine. When this light bulb was on this side, this lens, it actually formed a real image somewhere, let's say, over here. I mean, there is nothing physical here, but the real image formed here. And when you are looking through the lens, the light that you are seeing coming from this looked like it was coming from this location in space. Now, this is demonstrating more concretely that there is something here that's not at any other place. Like, it's out of focus here, it's in focus here. So this is something that's projecting an image. Projecting it so that you can project it on a screen, make it go through diffuse reflection and see it from other places. That's something that's only possible with a real image and not with a virtual image. It's because the distinction between real and virtual image is that for real image, you can do this. You can draw a ray of light coming from the light bulb through the optical element, and it actually ends up at some place where the image is. When you look at this, let me turn on the lights back.
Here is another example of a real image formed by the Fresnel lens on a white screen immediately behind it. You can see the bright sky, building, and the cars occasionally passing by. The image is formed at a fixed distance. So if we move the lens closer or farther, the image will go out of focus. I can do some tilting while the image remains in focus. And without the white screen to diffusely reflect the light that's forming the image, we can't quite see the image unless you are positioned correctly relative to the lens. Now, back to the in-class demonstration.
Maybe, oh, it's bright enough to actually do that. When you look at this virtual image from this mirror, the light rays, they do appear to be coming from here, but it doesn't actually come from here. When you have a real image, sort of imagine when it was the other way around, the light rays do appear to be coming from this point image. That's what image is. And they actually do. They actually do come from here. So that's the distinction between a real and virtual image. In both cases, you would say image is where light rays appear to come from. And I guess it's better to define just the word real. When you have a real image, not only the light rays appear to come from there, the light rays actually come from the image. I mean, originally from the object, but through the intermediate step, it actually does come from the image. So light rays actually come from doesn't sound quite right. I want to say go through. Actually go through the image. Actually go through image. So that's the distinction. Virtual would be the negation of this. Light rays don't actually go through the image. Like here, the virtual image, no real light rays ever went through this point. So, so when you have a virtual image, like, okay. When you see something like this, you see a virtual image of this light bulb on the other side of the lens. Like the light rays appear to come from somewhere here, right? And if I place the screen anywhere here, you wouldn't see what you're seeing on the whiteboard before, because no light rays are actually here that you are seeing as a virtual image here. Okay? So that's the distinction. I want to draw that distinction now and start developing your intuition, because having this intuition will make it easier for you when you start mentioning some sign conventions and doing all this math. So what intuition is helpful for is it tells you when you are wrong. Also tells you when you are right, but more importantly, it tells you when you are wrong so that you can sort of look for what's wrong. Once you have a clear understanding of what real image is, what virtual image is, that will make it easier for you to apply the sign rules that we are going to cover soon.
I think the biggest value of the simulation is kind of playing with it, noticing what's unusual about it, and kind of learning from that. And what I'm excited about this simulation is it kind of intuitively shows you some of the things you can, that takes a lot of work kind of sketching out if you are sketching things. And this new version of the simulation also has a version for mirror, which I hope kind of illustrates the reason I prefer to work with the lenses. So with the mirrors, when you're drawing ray diagrams for the mirror, it'll tend to get very messy, because you can have this kind of overlapping thing and distinguishing between outgoing rays and incoming rays. So sometimes it becomes difficult. That's one of the reasons I prefer the lens description. And almost everything you can do with the mirror, there's an analog in the lens version. So I'm gonna be working with the lens. I guess the one thing that might be worthwhile pointing out in the mirror version, because I think I've seen this in some students in the past. Sometimes people want to memorize rules that are based on whether something is convex or concave. And I will tell you that that'll lead to confusion, because things that are convex in lenses does very different things from mirrors that are convex. So if you're trying to memorize things based on whether things are convex or concave, you gotta flip them around for lenses and mirrors. And what I would recommend, and I think you see me giving this recommendation in lecture, when you're memorizing rules like a sign convention, memorize it based on converging or diverging. Leaving it to your intuition whether a particular object is diverging or converging. And that kind of, it's a kind of factoring kind of thing, refactoring kind of thing, refactoring your knowledge. So in terms of dealing with the geometric optics, you know what to do when you have a converging arrangement and when you have a diverging arrangement. And in terms of whether concave shaped mirror is converging or diverging, well, that's the other piece that I would recommend having as a separate package. So let me just work with the lenses. And this is already useful to show a number of things. One is, so right now this setting is set up to show marginal rays. And when you see me do ray diagrams, you won't see me draw marginal rays. Partly because it's hard to know with the marginal rays in which way they should bend. Most often we'll be drawing principal rays, because principal rays have a very easy to follow rules that I can use to draw them. Now, sometimes with the principal rays, you will have a diagram that maybe looks a little bit unnatural. Like this ray here, it's not even hitting the lens and it's still bending. It's because principal rays it's just a mathematical tool. It's not necessarily indicating that any kind of actual physical picture, depending on the size of the lens. Oh wait, that's wrong diameter. Wait, is that no, that's, well, why? Well, anyways, depending on the size of the lens, the principal ray may be hitting the lens, or it might not. Either way, what the principal ray tells you, it doesn't change. You can see it here. As I change the diameter, the location of the image doesn't change. And here, what I will say is the most physically correct view is actually this one, the many rays picture. And this is really useful when you're drawing a ray diagram for the virtual object. I think you see me do that in one of the lectures. When you're drawing ray diagram for virtual object, that's when you use the fact that many of the rays that you are not drawing, when you do principal ray diagrams, the rays that you don't draw, they are still there. And so that's the real physical picture, that there's an infinite number of rays going through the lens that originate from a point. And the principal rays are simply what we draw to help us locate the image. And I guess one last thing that might be worth noting while I have the simulation up is something kind of a change to note, and I guess note what doesn't change as you change the size of the lens. So as you make the lens smaller versus larger, so this is a simulation. It's simulating things that are programmed in, and it's programmed to illustrate a certain thing. Note how as I make the diameter of the lens smaller, the extent of the image that's being formed here, it doesn't change. Just because I have a smaller lens, that doesn't mean only a smaller portion of the object gets imaged. The entire object still gets imaged. And as I make the diameter larger, what does change is the brightness of the image. It's kind of indicating, in this many rays view, how many of these many physical rays actually go through the lens and forms the image here. With a smaller diameter, less of that happens. That's why your image is so faint. And in the lab, you will get to see this in a more fun way, in that with this diameter, I think sometimes it's kind of easy to see. All right, so you still have the same issue lens. It's a matter of how much light you catch. So that's why the location and the extent of the image doesn't change. In the lab, you can cover half of the lens, as in cover like upper half or lower half, and see what kind of change, if at all, happens with the image. So this simulation isn't made to do that. It doesn't. I tested it before. It doesn't. It doesn't give me a barrier that I can move around. So, anyways, so I would. It's a great tool to kind of play around, see if the kind of the intuitions you have about ray diagrams match. And I'll just leave that there.
So what we are going to do today is we are going to look at it from a little bit of a higher level. So for example, when we have a mirror setup, and let's say I have a curved mirror, and then I'm going to assume that somehow I know where the focal point is. I mean, if you remember last Tuesday's lecture, then if this is radius of curvature, then the focal point should be here, right? But whether you remember that or not, we'll just say, all right, here's my focal point. This is the focal distance f. And so this is the starting point that I want to use. So this is for the mirror. And if we have lens, then it would be something similar, where if I have a convex lens, that should be converging. Then, so last time we went through how, given the radius of curvature, So given some object somewhere where the image would form, I stumble through that somehow. I will change how I do it. Anyways, so for today, I want to say we simply know the focal length. Maybe somebody else calculated it for me, or maybe I just measured it. However the setup is, I simply know what the focal length of this lens is. Good? So that's what I mean by high level. I just want to start up from this knowledge that that these two common optical elements, curved mirror and lens, has some focal point, and we are going to use that as a starting place to do some basic, but not basic, to do some geometric optics, starting with the ray tracing. So I think in the way of introduction, the place I should start from is ray tracing. So it's a way of analyzing how does this optical element affect a ray of light that's interacting with it. So in the case of mirror, it's reflecting from it. In the case of lens, it's going through it. So let's just imagine that we have a light source somewhere, or we have some kind of source of light. Who knows what it is? And this source of light, it's sending out light in all directions. So I'm not going to draw all those rays of light. I did it last time. But there are two special rays that I want to look at that's going to interact with this mirror, that I can actually say exactly what will happen with it without doing complicated calculation. One of those special rays is a ray of light that's coming from here, and it's going parallel to the axis. So for this ray of light, does anyone remember from what we covered on Tuesday, after reflecting from mirror, in what direction this should go? Yeah, towards the focal point and through it, right? So yeah, so this is one of those special rays where I don't really have to go through a whole law of reflection, all this stuff. This is the definition of focal point. If any light ray came in parallel to the axis, it's reasonably near, then after reflecting from it, it should go through the focal point. If it doesn't, then you did something wrong. So that's one special ray. Let me draw the second special ray with a different color. It's a special ray that reflects from this point, the vertex of the mirror. So, yeah. So if this ray is coming in this way, you kind of know this angle. That's the angle of incidence. And because this is a vertical surface, you can immediately see what the reflected angle would be. So after reflecting, it goes like, it reflects off as if it's reflecting from a flat mirror, right? So those are the two special rays. And here's the reason we are paying attention to it. If I extend these rays out enough, then many times you will see that they eventually intersect. And where these rays intersect is where the image of this forms. So if you have, usually we use arrows to indicate image. So if I have an arrow, that's, arrows as an object. So if I have this object, then if I'm standing here looking in the mirror, then this, the image of this would appear here. So as I look at the mirror, what you are seeing is this image here. That's what you would see. And that's what you see when you look at this giant curved mirror. So the object would be everything that's on this side of the room that you are seeing through the mirror. And where those objects appear to be would be somewhere around here, upside down, as you kind of see from this figure here. Good question?
Yeah, so shouldn't be the size of the object be smaller than the first one?
It depends on where it is. So Samuel is asking, shouldn't this image be smaller than this? Because that's kind of what you're used to seeing here, right? Yeah, so it depends on the distance. I will say, so we'll go over that actually in about 10 minutes. But if this is farther away, then yes, image will be smaller. But as this gets closer up to the focal point, this image will get bigger and bigger. And something different will happen once this crosses the focal point. Good? So I want you to draw this picture with a mirror, but I will tell you one thing. I'm going to stay as far away from mirror as possible. It's mainly because drawing diagrams with the mirror is painful. The rays overlap on top of each other. I keep erasing lines. So whenever there's a problem dealing with a curved mirror, my preference is to rewrite the problem into a equivalent version that can be represented with the lens. So when you look at chapter 2 problem set, you will notice that I didn't give you a lot of mirror questions that are in the OpenStax University Physics. It's because I hate those questions. And if you want to work those out, the first thing you would do is you would rewrite it so that you have the lens version of the essentially same question. So, okay, so let me move on to lens, and we'll do something similar to this for the lens. So I have focal point here. And let's say I have my object, some kind of source of light that's over here. Then the first special ray that I drew for mirror, so let's just try doing the same thing. So there's going to be a ray of, so there's many rays of light. Of those, I'm picking just the one that happens to be parallel to the axis. And as this ray goes through the lens, it'll somehow refract as it goes through. And this is once again what I mean by high level. I'm not concerning myself with the details of refraction at each surface. The only fact I have to know is where the focal point is. So where does this ray go? Through the focal point. That is the definition of focal point. That if any ray came in parallel, then they go through this point. All right, so that's one special ray. So looking at this again, I guess second special ray should go through the middle of the lens. And what do you think the lens version of what you saw here would be? As the second special ray goes through the middle of the lens, what happens to it? Yeah, straight through, nothing. So imagine this is, so here it's all vertical surface, so it's like a glass pane. When you are looking through glass, there could be a little bit of a displacement. But if the glass is very thin, there wouldn't be even that. So that's what's going on here. So this second special ray will go straight. Am I drawing this right? All right. So when you do proper ray tracing, I recommend that you do it with a ruler, straight edge. So these are apparently crossing here. So that's where the image of this forms. So same thing as what we saw here before. If I had object here, an arrow again, then, so I guess when I draw this image, this is really what I mean. If you imagine doing this drawing for every other point on this arrow, you will see that they all end up along this same vertical line. So, so I'm just not going through all that tedious work, but sort of trusting that it'll happen and drawing this image, having verified only the tip. But if I, for example, if I pick this point here and go through the ray tracing, then the focus should form somewhere here. Good? Okay, so that's the quick introduction to ray tracing. There's, let me write down the names since you might be asked in those terms. These are what we call principal rays. These are the special rays that we happen to know how they bend as they go through the lens. Or we happen to know how they reflect as they reflect from mirror. There are many other rays that goes through the lens. For example, there's this ray. There should be a ray that goes through this point of the lens because it's transparent, right? So if I have this ray that's going through this point in the lens, anybody know how this bends? It wouldn't bend up. It would bend downward. Yeah. Do you know any other point that this ray, after going through the lens, must go through?
The corresponding point of
Yeah, this point. Because I know image forms here. And the fact that this is image means any ray that started here, went through the lens, has to go through that point. So now, the thing is, I couldn't have done this right from the beginning. Because before I drew these two rays, I didn't know where the image was. So that's the function of this principal ray. It helps you find the image. And once you have the image, then you can draw as many rays as you want to draw. But you don't want to waste too much time doing that. So these two principal rays that I drew, they allow you to find the image. And once you find the image, then you can do other things like drawing this additional ray if you wanted to draw it. There is one more thing we can do before we move on. It's sometimes you will hear references to 3 principal rays instead of the 2 that I just drew. I guess it might have come up in high school physics, whatever. So if you are looking for a 3rd principal ray, this is how you would do it. So I drew only one point as the focal point. And a lot of times when people draw lenses, you will actually see them mark 2 focal points. One at f distance on one side, and the other at the same distance on the other side. Did I? I might have not drawn it quite right. Let me, I don't know, it's hard to do it without straight edge. Does it look roughly the same distance? Roughly, close enough. Okay, so the 3rd principal ray, which if you want to draw it, you can. It looks like this. The ray comes from this point. It's the ray that goes through the focal point on the other side. I don't know if there's a name for it. 2nd focal point goes through here. And at some point, it'll hit the lens, hopefully. And as it goes through the lens, how do you think this ray should bend intuitively? Goes out parallel, you mean?
Sorry.
Yeah. Goes out so that it's parallel to the axis. And when you draw this all properly with rulers and whatnot, you will see that it goes through the same point here. So it's a redundant, it's unnecessary. That's why when I draw ray tracing, I usually don't draw this one, especially when I'm doing freehand without any straight edge, because I'm afraid that it won't come to the same point. But this is the 3rd principal ray. If you needed to draw it somehow, then it would be the ray that goes through the focal point here. Okay, any questions? All right, so drawing rays this way, it lets you find where the image is graphically. That's all nice. But this is terrible for most of the problem solving, because you don't want to be drawing these figures every single time. And you have to draw it accurately. You can't do what I was just doing now. So that's why there's a formula that's derived. And you can actually derive it yourself too, relatively easily from, I believe, simple consideration. So it's a formula that relates these quantities to each other. So I already labeled one of those quantities, focal length. The other 2 quantities, let me get rid of this. The other 2 quantities are the object distance, usually labeled DO. I think we were using this label last time for something a little bit different. And the 3rd quantity is the image distance. So it's a geometry question. So how do you relate these 1, 2, 3 variables? There's one single equation that'll have all those 3 things in it. So normally you would know the focal length, you would determine the object distance, and then from there you can get the image distance. When you have all this figure, hopefully you have a sense that you do have all the information here. This is a completely determined system. The only thing that's remaining is for you to go through the geometry and from the geometry sort of work out that expression. So let me do it this way. So I'm going to draw a few triangles that I feel will be useful to me. I feel that this triangle, let's see. I feel that this triangle will be useful to me. Any guesses why? Yeah, I know one side, DO, object. So I guess I better label this. This would be the height of the object. So HO. So it's, it's a triangle where I know some of the sides, and this is related to what this is. And let me label one more triangle that I feel would be useful to me. And I guess it's the counterpart to this. I'm going to draw this one. This triangle here. This is another right triangle. So DI is known here, or it's labeled there. And I guess this is the height of the image, right? So let me call this HI.
So should that be negative?
Let me give this some thought. Right now, I'm just doing geometry. So in geometry, it's a length, so everything is positive. There's something I'm missing here. What am I missing? Oh, I don't have any triangle that involves the focal length. I need to have a triangle that involves focal length. So, I guess this is the only triangle that does that. Right? This triangle involves the focal length and this height that we already labeled. Well, let me start writing down the equation, and then I will see what I'm missing. So these two triangles share this one side. So that lets me say this. I guess I need to start labeling some angles. I have this angle. Let me label the theta 1. And I have this angle. Let me label the theta 2. So what I can say is d naught times tangent of theta 1. O times tangent of theta 1, which will give me this height here, is equal to the focal length times tangent of theta 2. So focal length times tangent of theta 2. All right, I have two unknowns, one equation. That's a little hopeless. So I think my goal will be trying to get rid of these angle thetas. So I'm staring at this, looking at, all right, what else has angle theta 2? And I see this triangle here. That should have the same angle theta 2. Right? And let's see, I have the height labeled as HI, so let me leave that there. Can we write down an expression for this? What is it? Yeah, DI minus F. All right, so we can say that tangent of theta 2 is equal to the height over this, HI over DI minus F. Or I guess I could keep this on. So it's focal length times tangent of theta 2. So HI over DI minus F. All right, I still have two unknowns. I have HI and theta 1. So that didn't really help me, did it? Can I write down one more equation that doesn't introduce any more unknown? Maybe has only HI in it, maybe has only tan theta 1 in it.
From two similar triangles.
Which similar triangles?
The no HI.
Yeah. So this is a similar triangle 1. What's the other one?
On the bottom.
Yeah, it's this other triangle here. They are similar triangles. Stare at it long enough, then you can convince yourself, these angles are the same. It's right triangle, so the other angles must be the same, so it's similar. So you can write down the ratio of the sides are equal because it's similar triangle. You can say, let's write it down this way. DO over HO, DO over HO is equal to DI over HI. Which means we could solve this for HI and plug it in there. When we do that, this is what we get, F times, I should actually solve it for HI. So HI is equal to DI over DO times HO. Yeah. So this is F times DI over DO times HO. I think I did something with the HO earlier. HO was related to tangent theta 1. So in fact, I think this entire expression was supposed to be HO, right? DO times tangent of theta 1. Yeah. So okay, so what I have is, oh wait, I skipped something, right? Yeah, okay, yeah, let me write that in. Times di minus f. All right, so, okay, let me write down the cleaned up version. So this is the cleaned up version that expresses what I've been saying out loud, that HO is equal to all of this. F times di HO over DO times di minus f. So you see that height of the object cancels out. I don't have to worry about it anymore. And wow, this is one complicated expression. So you could, if you hate fractions, you could, so 1 is equal to that. So if you hate fractions, you could rewrite it this way. DO times di minus f is equal to f times di. Not that simple, right? So let me expand out the left-hand side, and one way to simplify this expression will become visible. When I expand out the left-hand side, it's a DO times DI, and it's minus DO times F. I'm going to move that off to the other side. So DO times DI is equal to F times DI plus F times DO. F times DO. I don't know if anyone notices the thing I'm noticing. You have 3 variables. These are all possible combinations of multiplying only 2 out of the 3 together. So if you take this and multiply the whole thing by 1 over product of all 3, 1 over F DO DI, then for each one of those terms, 2 out of 3 will get canceled out. And when you do that, you get this whole thing is equal to this is DO and DI cancel out, and you get 1 over F. 1 over focal length is equal to focal length and image distance cancels out. So 1 over object distance plus, and so focal length and object distance cancels out, so 1 over image distance. It's a remarkably simple expression that you are going to use a lot. So this expression represents the same mathematics, the same information as what you got with ray tracing, except this is a geometry and art project. This is an algebra problem. So this, for many of you, this will be so much easier than this geometry project. But these are two different ways of representing the same thing. I want you to be able to switch back and forth between the two. For most of the homework problems you will work on, that's due on Tuesday, this will be one of your most useful expression. And I did this for lens. It works for mirror as well. I'm just not doing it here because the figure will just be so messy that I don't want to do it. But this relationship holds exactly the same for mirror as it does for lens. So example 1 is, it's with a converging lens. And the object distance is greater than the focal length. So here's the lens. If this is the focal length, then the object is placed somewhere out here, for example. And you guys saw the example 2 and 3, so we'll get to those. But let me just go through each example one at a time. So when you have a question like this, technically you can do it without drawing any diagrams. It's a sort of, I don't know, trusting this equation. So you could do this question by, all right, you have object distance. This is object distance here. Let me get some numbers to plug in so that I have something concrete. I guess let's say that the focal length is 10 centimeters. And object distance, does it look like 15 centimeters maybe? Yes, I want to be close. It doesn't have to be exact, but I just want to be close. 15 centimeters. So the question would be, I think the image is going to form somewhere here. There will be image here. So the question is, all right, how far is the image distance? Yeah. And if you trust this equation, then this is actually a pretty easy question to answer. You have one equation, one unknown, so you go through algebra and solve it. Let me do that quickly. So I have, where do I want to? Let me do the algebra here. Wait, let me do the algebra here. So this is my lens equation, 1 over dO plus 1 over di is equal to 1 over f. I want to solve for di, so move this over. So I get 1 over di is equal to 1 over f minus 1 over dO. I want to take the reciprocal, so I guess I should combine this fraction here. This is equal to, so the common denominator, f times dO, and so dO times 1, dO minus f times 1, f. That's the combined fraction. Now take the reciprocal, that will give you the image distance. So the image distance, di, is equal to f times dO over dO minus f. You will do this algebra so many times as you're going through that homework set, maybe about a dozen times or so, which is good. I mean, algebra, I feel like there's always something to gain from algebra practice. Let me plug in the numbers. I'm going to skip the units because they will simply cancel out. The centimeters will cancel out. So I'll say 10 times 15. Oh, wait. Well, one factor of centimeters will cancel out, and I'll be left with one remaining factor of centimeters. Divided by 15 minus 10 centimeters. So it's 150 divided by 5, 30 centimeters. All right, so that's my answer for the image distance. So apparently, if I draw this correctly, my image is supposed to be at somewhere here. So this is how far away my image will be. Di equal to 30 centimeters. And that's okay as far as finding how far away the image will be. And if you're trying to do the demos that I showed you last time where I was trying to form a focused image of the filament on the whiteboard, that's kind of all you need. But there's one thing that's lacking here. And that lacking thing is, suppose someone asked you this question. The image that's going to form somewhere here, is it going to be an upright image or inverted image? Some of you know from your reading it's inverted. How do you know it's inverted? You are bringing in a formula that I have not yet introduced. So D-Lang is trying to tell me that linear magnification M is given by minus di over do. And since this is negative, but we are going to get to this. So suppose you didn't know this formula yet because we haven't talked about it yet.
By the retrace, by the geometry.
Yeah, so that's what I'm going to do. I'm actually going to go into ray tracing. Because if you're trying to, based on this thin lens equation, try to figure out all the details about this image, there are some things that you are not going to be able to figure out. So the thin lens equation, it gives you the distance. That's what it's in terms of, that's what it gives. But everything else, it really only comes from drawing the diagram. So this is why even though I know where the image will be, kinda, I'm going to do my ray tracing to locate the image still. So let me draw my two principal rays. As a reminder, so I guess you can define three principal rays, but I usually draw only two because I'm afraid the third one won't come out right. So I'll only draw two. So the first ray comes in parallel, and how does it go out? So first ray, it comes in parallel to the axis, and how does it go out after going through the lens? Yeah, it goes through the focal point and goes through focal point. So let me draw that. Trying to draw this as accurately as possible. All right, we'll see how that goes. Second is it goes through middle of lens, and as it goes through the middle of the lens, do people remember how it goes? Yeah, goes through the middle. Let's say straight. It doesn't bend. So. Somewhere here. I don't know, good enough. So if you did it with a straight edge and did it with a perfect precision, then you should end up somewhere here. And what that intersection, that point tells you is that this point, the light rays from this point, they all come together to a focus here. So when you are looking at these light rays from here, these light rays will look like they are coming from this point. So you will see a sharp, real image at this point. So let me sketch out the rest of the image here. So what the rest of the image will look like is this tip of the arrow and the rest of the arrow. So this is what the image looks like. And that's why it's inverted. And once you have this diagram, then you have what you need to derive the magnification formula that D-Lang knew from reading. So let me draw the auxiliary figures that will let you derive the magnification formula. These are the auxiliary figures. This triangle here, and this triangle here. By the way, everyone here familiar with the concept of magnification? Like making something greater by some factor. So if I want you to define a magnification for this lens, how would you want to define it? Like, let's see. Yeah, let me just leave it there. So how would you want to define magnification? M. What two things do you have whose size you are concerned with?
The size of the object you're looking at,
Yeah, size of the object.
the distance you are with.
Well, what do you mean about what do you mean by distance?
I guess I'm just thinking of actually looking through a magnifying glass, not to adjust a certain distance in order to get it to be a certain size.
Yeah, we'll talk about that. What you see through magnifying glass, that's going to be something called the angular magnification. Here, we are dealing with the linear magnification. We are dealing with, okay, so I have this object of a certain size. And when I look through this lens here, this object, whatever I see through the lens, it doesn't appear to be this thing of, I don't know, 10 centimeters or whatever. One, its location will change. But after having accounted for that, what I look through this lens will appear to be an actually different size. So what is it that I'm seeing when I look through the lens? I'm not really seeing the object, right?
Yeah.
What am I seeing?
The virtual.
Not virtual image. Well, it's this image, right? Whenever I look through the lens, what my eyes perceive is the image. It can be virtual, it can be real. So what I'm seeing is this image here. So when I'm talking about the magnification, I would want to know how the size of the object was magnified into the size of the image. So let me just give it some labels. Let's say this is my object height. And let's say this is my image height of the image. Good? So I might say my magnification M is that ratio of these two. Ratio of the height of the image divided by height of the object. Good? And we are actually going to allow this magnification to be positive or negative. So this HI here as drawn, this should actually be a negative number because it's going, the object started out upright and it's going below the axis. So we are going to say this is a negative number. When we do it that way, this magnification can be used to tell us if an image is upright or inverted. Okay, so this is the definition we are starting out with, but this will be very inconvenient definition to use because then you will have to know the size of the object, you will have to know the size of the image. And do you feel like this magnification should depend on the size of the object? Like if I used half as tall of an arrow, would my magnification still be the same? Right? Yeah, the image will be half as tall, so that magnification will be the same, right? So even though this is how we define it, we won't really use this a lot. And this is where these auxiliary figures are helpful. This right triangle here and this right triangle here, they share a feature in that one side of this right triangle is the height of the object, and one side of this right triangle is the height of the image. How are these two triangles related? Can you see anything that says those are not just the two random triangles, they actually have some relationship to each other? Not congruent, similar. Somebody said similar. Yeah, similar, right? They are different sizes, But you see that these two angles are the same. So it's a right triangle, so all the other angles are the same, so they are similar triangles. Which means if you know the other sides, and we do, this side here is the object distance. And this side here is the image distance. You can say that the ratio of the sides are the same. Or I guess making things easy for myself, I can say ratio of this side to that side is equal to ratio of this side to this side. Okay? So we would say this magnification, this is the definition, but we would say, all right, we can see that it's numerically equal to image distance over the object distance. Yep. Now you might wonder, if you are looking at the formula in the textbook, other than this swapped error, it has this minus sign. Should we have a minus sign here? Yeah. So here I said that the image height, I'm going to let that be negative. Here, can I just say I will let image distance be negative? No, because looking at the thin lens equation, image distance was positive. And this positive sign actually has a meaning that we are going to go over really soon. So here, image distance is going to be a positive number. So we put the negative sign with the formula. That's where this formula comes from.